Hello, everyone. So this is Ayon from NEC Labs, and I'll be talking about situations where first responders need to be tracked, for example, like firefighters and other people working in emergency situations like public safety. There is no real infrastructure to track them, and then how do you use something that I'm going to present called TrackIO, where I can make the tracking of these first responders very efficient. This is a joint work with a very enterprising intern that we had, Ashutosh from University of Illinois, and my colleagues Karthikeyan and Sampath from NEC. So going into the current situation where we see a lot of first responders or the emergency responders in the public safety domain getting trapped. And sometimes these are very fatal. And as we see in the newspapers again and again, that in case of rescue operations or wherever people are entrapped after severe earthquakes or hurricanes, it's very difficult to figure those people out where the actual rescuers are. So, and if you see this plot, it's very evident that the numbers are not coming down in spite of the fact that we have a lot of new technologies coming out where we have mechanisms to track them, but they don't prove to be quite effective because the numbers doesn't seem so. So one of the fundamental bottlenecks that happens to be the case is we have lack of tracking of these emergency responders in real time. So since we cannot track them in real time, we cannot take in situ actions. For example, the fire chief or the commander sitting outside cannot give very specific instructions, for example, to help a certain colleague who is probably not very healthy at that point of time because maybe he has injuries or something. So timely actions could not be taken, and that sometimes leads to very fatal incidents and leading to death of some of the emergency responders. So this is a very critical problem that needs to be handled, and we really don't have a lot of very efficient solutions to handle this problem. So what are the key problems in trying to solve this, like what could be used in this situation? For example, the first thing that we don't have GPS indoors. So whenever these firefighters or the first responders go in the building to rescue, they don't have access to GPS. And as a result of the fact, we don't know where exactly they are. And there are commercial solutions that use inertial sensors like IMUs, accelerometers, or gyroscopes, but they drift a lot. So it could not be used as a reliable solution that works for a very long time. For example, about an hour, for let's say, for the time it takes the rescue operation to take place. We don't have access to deployed infrastructure like Wi-Fi or Bluetooth beacons where I can quite easily track those people inside the building. So we don't have the luxury of assuming this kind of infrastructure that is inside the building, or they might be compromised, or they might be burnt, or we just don't have access to that. And this information is needed at real time, because based on that information, I'm saying there is a lot of actions that had needed to be taken, and we have interviewed a lot of people like the firefighters and all. So they need to take in situ decisions, which is very crucial for the survival of the rescue operators. So what we get after this is we just get a global position that we know maybe the firefighter is in the 4th floor of the building or the 5th floor of the building, but we don't have any micro scale knowledge about the exact location of these people. And what we try to do is try to figure out what can be done in order to bring infrastructure to the building without relying on the pre-existing infrastructure that could be already inside the building. So before delving deeper, many of you might be familiar with wireless positioning, but I just want to give a basic idea about how wireless positioning works. So let's say we have a wireless device that needs to be localized, and for that, we have a probing device at a known location, say X1, Y1. And what we need to do is we need to range this device from a known location, and this technique or the operation is known as ranging. And this ranging is very fundamental to wireless positioning, where you need to know the distance of that particular device from a known location. And one range is not sufficient because it is going to solve for, it could be anywhere inside the circle or on the circle, in the circumference of the circle. So you need multiple points. That is basically multiple locations of the probing device. At least 3 if you are trying to solve it in 3D, or 4 in 3 in case of 2D, and 4 in case of 3D. So basically, you have known locations of these probing devices, and from there you know the range of the wireless device, and from there you can solve for where the wireless device is inside the building. So in our case, our wireless device is indoors because the emergency responder is inside the building, and the performance of the localization technique depends on several things. One important thing is the precision of the range. Right? There are lots of technologies. For example, you can use Wi-Fi to determine what is the range of that particular device. But in our case, we chose the ultra-wideband technique, which is relatively a higher frequency technology, but at the same time, it gives a good enough accuracy at the level of tens of centimeters. That is the precision of the range that we are obtaining for the wireless device. Because of the higher frequency, we have lower penetrability, but that is something that we are also handling, that I'm going to explain in the remaining part of the talk. So apart from this, what we also need is diversity, like geometrical diversity of these probing points. It cannot be, we cannot range all the points from a place where all those points are clustered, where all the probing points are clustered. So we need good enough diversity. So for that, what we utilize is UAVs, like our drones. That already is equipped with a UWB node, and that can go around and very freely range the wireless devices. And not only it is ranging one device, but there could be multiple devices. Some of them could be blocked, and from one location it is not natural to range all of the devices. So a flexibility on the part of the drone helps in order to range all the devices. Some of them could be non-line of sight, some of them could be line of sight, and so on. Right? So UAV seems to be a very natural choice here. So these are the two main pillars that we are basing our solution on, and the algorithmic part is something that I'm going to come later on. So how does the TrackIO solution look like? So there's a building on fire, and the fire responders go, the first responders go there and have the truck. We launch the UAV there. All I'm doing is, it has a UWB radio equipped on it, which is ranging the UWB radios that are on the equipped with the first responders themselves. And what we are trying to give them is, for example, a dashboard or a UI that could be with the fire chief or the commander who is outside the building, and he could see on real time what are the location of these people and different parts of the building. On the building map, for example. And in case if we don't have a building map, we can put the personnels in the perimeter of the building. At least we know their relative locations, or what personnels are close to each other, so that they can talk to each other or help themselves out in case somebody goes unconscious or something like that. So this is the vision that we are trying to realize. And we are developing the solution towards this vision. And what we have is, the drone goes around the building, and the chief can control, who is controlling, he can see the drone actually moving and the firefighters being localized in real time. And this is one snapshot of the UWB beacon that we are using. So is my picture. I'm basically being localized from a drone that is flying outside the building. So this drone has a UWB beacon equipped on it, and it's actually moving, forming a synthetic aperture. And the ranging technique that we are using, it's much more involved. The protocol I'm not explaining. It's a UWB uses a two-way ranging based on the time of flight information, and it seems to be pretty precise. The precision is on the order of tens of centimeters. So let's look at the solution. So you have a building like this, and you have firefighters scattered around inside, and you have the drone that moves and forms a synthetic aperture, collecting the ranges whenever it moves. And it also has the GPS coordinates. It is recording at every point wherever it is moving across. So at every point I have a GPS location as well as ranges that are being recorded to all the UWB devices inside the building. And what we do is, we just trilaterate the same way I just explained a little while ago. And it works fine for static nodes. It looks like a very simple solution. You fly the drone, and somebody is sitting inside, you collect the ranges, and you just trilaterate and you know the location of the guy with pretty good accuracy, less than a meter accuracy. But now imagine a situation where there is a fire and emergency responders going, so everything is mobile, nobody is static, and the firefighter is not going to wait till the drone moves and creates a synthetic aperture, right? So there are several challenges. The first one being mobility. So what happens if the node is mobile? So what I'm doing is I'm sampling the ranges at different locations, and the guy has already moved. So the trilateration is going to solve for a location which is actually not any of the locations where that belonging to the trajectory of the user or the first responder. The other thing could be the velocity could be constant. He could move in the same direction, or he could take turns also. Then suddenly the complexity of the solution also increases. What do you do in those cases? And the other thing is as I said, it's a high frequency technology. The penetrability is limited. So what do you do in case to increase the reach? Because the distance from the drone to the first hop, for example, the nearby guys could be say 40 to 50 meters, but it could be the people could be more deep indoors. How do you get to reach them? So these are the three things that are the basic challenges, and the protocols and the other development or the other algorithms are mentioned in details in the paper. I'm going to explain how we are tackling these kind of situations. So the first is the mobile node. So we solve for the velocity. So instead of solving for the location itself, we are assuming if the velocity is sort of constant in a given direction. So it's just simple kinematic equations we are using. So Cxi and Cy and Cz are the location of the drone, and Xi, Yi, and Zi is the location of the first responder that we are going to solve for. And we know the timestamps, and we solve for the initial location of the first responder as well as the velocity. So this gives me the initial location of the first responder as well as their velocities, and then we just use simple kinematic equations to find out their trajectories. So just using, instead of naive multilateration, if you are incorporating velocity vectors in the solution, the performance of the solution increases much better. As you see, if somebody is running, we are getting about 3.6 times improvement in terms of the localization error. The next thing is that how do you tackle turns? So as we see, if the aperture is very small, the geometrical diversity is also very limited. So in that case, the localization accuracy becomes very poor. But if it is pretty big, the velocity might have changed within that time. So it will very slowly adapt to the changes in velocity. So what we need to do is we basically look at the solver's error, because whenever we are doing the multilateration, the solver fits for the best possible fits for the location of the user as well as the velocity. So what we do is that while solving this, we also track the residual of the trilateration. And if you see this plot is very interesting, is whenever the user starts taking a turn, the residual actually increases. That hints us that the velocity probably has changed and the user has probably taken a turn. So this is the time wherever I have the lower residuals and the residuals suddenly go up, that indicates me that the velocity has probably changed. What we do is that we reset the aperture from that point of time and then continue the building of the history again. So this makes sure that the aperture that we are using is pure in terms of uniform velocity. So higher residual errors give us a very good indicator for triggering the aperture reset. And the other thing is the limited reachability. So what we do is that we modify the UWB protocol to incorporate multi-hop ranging. So this guy could not be reached directly from the drone. So we modify the existing UWB protocol to make sure that the people who are directly reachable from the drone are reached first, and then they broadcast whether there is somebody in the second hop such that this guy can respond to them, and this guy basically gets trilaterated with respect to the other three guys whose location is already being known from the initial thing that I explained. So in this way, we basically have hop 1, hop 2, and we can probably go to one more hop in order to increase the reachability, but in all practical cases, it probably covers most part of the building. For example, in the building, this is the NEC Labs building in Princeton, and we cover by flying the drone in one side of the building, we cover about 1,300 square meters. And in case the other side needs to be covered, we could fly one more drone on the other side of the building as well. And about the performance, if you see on the left-hand side, the CDF shows the localization error in different situations. The first one is the static case, where all the nodes are static, and the rest are mobile. And in the mobile case, we increase the complexity about how they move. For example, if they move in a straight line, the velocity is sort of uniform. So the performance is slightly better than the other two cases. For example, rectangles and triangles, where they take more number of turns. But by using the adaptive aperture, we try to make sure that even if there are turns, the velocity vector is correctly calculated at right points of time when the turn happens. So this is a picture of the actual prototype that we were using for the experiments, and now this has changed. We are going towards the commercialization of the technology. This is a DJI drone that has this node that we are showing on the right-hand side. It just has a Raspberry Pi equipped with a GPS, and that collects the data from the UWB node, which ranges the first responders inside the building. And the drone is like, it is controlled in a semi-automatic way. We give the trajectory, and then the drone follows the same trajectory and collects the ranges on one side of the building. So some of the salient points here what is interesting is that if you don't have infrastructure inside the building, that is a point that I'm stressing on, is that we don't need any pre-deployed infrastructure. The drone gives you the infrastructure and the freedom to fly around the building and off-the-shelf get the localization of the first responders inside. In case of static nodes as well as slightly mobile nodes, we could make the localization accuracy as good as 1 to a couple of meters. That is, the assumption is human mobility. If it is too fast, maybe the algorithms need to be more adaptive, or we might need to tune the algorithms a little bit. We have this multi-hop ranging, which makes the penetrability indoors much better. So we can go up to 2 or 3 hops that covers an entire building. And we have been talking about this solution to a lot of fire departments who have already shown very active interest in this technology. So there's a hope that we basically commercialize this thing, the research, into actual commercial prototypes, which is very inspiring for us. Thank you for listening. So if you want to look at a demo for our prototype, you can go to the link, neclabs.com/TrackIO. We have a nice video where we actually show a demo where our dummy first responder is being tracked from a drone. So thank you for your patience. Any questions? Hello.
So you mentioned a resolution of 2 meters, 1 to 2 meters, right? So it's more important to resolve in the z-axis, the vertical axis, than in the horizontal axis, because I guess you want to know which floor you're on, right? Does the algorithm allow for you to compute higher resolution along the vertical axis?
Yes, so in this case, the results, whatever we have presented, we first figure out which floor they are in, because once you move the drone in the vertical axis, based on whether you are receiving the ranges from the first responders, you know what floor they are in. And once you are in that floor, you basically try to move the drone in that plane. Suppose it is in the 4th floor, so I go to the 4th floor, and then in that horizontal plane, I fly the drone.
Hi. I was wondering how much do you depend on the GPS on the drones?
Yes,
and
it's a very good question.
On the GPS, how much it affects your system?
So it's a very good question, because what happens is the 10 centimeter range basically gets diluted by the location of the drone. If the drone is like 2 meters off, whatever the GPS reports, that becomes basically a 2 meter ranging error. So what we do is we use the drone's IMU as well as the GPS to get a fused version of the GPS. Because the drone knows how it is supposed to move and how it is going, so the fused version of the GPS is much better than the raw GPS. So in that way, it's still not perfect, but in that way, we basically try to tackle this problem. And then we do averaging in order to remove the noise.
Thank you.
Hi. So Curtis Heimerl, University of Washington. I'm a little, I guess thinking about it, my biggest concern is the drone itself. I mean, there's going to be like fire and explosions and people shooting water. And like, are the drones going to be consistent enough in, I mean, GPS is one feature, but like just maintaining a pattern in that kind of environment to be able to sustain?
So that's a very practical question. So we don't need a lot of space in order, because we can, assuming that we have some space in order to create the synthetic aperture, maybe 10 meters or 15 meters of open space, that could be enough. And we also have this multi-hop ranging, which we don't have to fly the drone on the face where, on the face of the building where there is a fire. So multi-hop ranging helps us to track anybody inside that floor. So we are limited to a small location where there is not enough dangers.
Okay, thank you.
Yeah, thank you.
Hi, Shiva from NYU. This is really cool work. My question is, what happens, I mean, how do you handle failures? So there could be firefighters that are caught in fires inside the building, or like caught in water, and you might not be able to track them. Does that happen?
Yes, so what happens currently is they have some sort of a dedicated infrastructure for talking to the fire chief. For example, a person A could already report that I am in distress. What was missing is that you don't know the micro location of that particular person so that you can help him directly. So this TrackIO tries to bring that kind of a solution to the already existing communication infrastructure, because they might have walkie-talkies or other technologies where public safety, operating in public safety bands in order to communicate with each other. So as long as I know where he is, I can ask others to go there and so on.
One more question, is that okay? And I saw that you actually deployed this in like in real settings, which is pretty great. I mean, so do you have a sense of like how impactful this actually is? Like how many, what percentage of, I mean, it can be very approximate, but what percentage of firefighters' lives is possibly saved because of this system?
I can't give a quantitative answer to this question, but as like we are starting off, right, just after the paper was done, we spoke to a couple of fire departments and they have shown active interest in testing out this. So we have some hope that this is something that is useful to public safety entities, but in the wild we have to see what exactly happens, what kind of performance do we get when there is an actual fire or an actual earthquake and people moving around, and there could be non-line of sight blockages. Those things are very crucial for this to actually work.
Thank you.
Okay, great. Let's thank the speaker.